We design and develop molecular catalysts that facilitate the deconstruction and reconstruction of chemical bonds, and we specifically target chemical reactions that involve hydrogen. In some respects, we take cues from nature and try to replicate some key design criteria in order to make synthetic catalysts. Much like an enzyme, we try to regulate the primary and secondary coordination sphere environment of a catalyst structure in order to impart unique reaction selectivity and catalytic activity. One of the overarching goals of this approach is to be able to make and break chemical bonds to hydrogen at will, either to store energy or alternatively to construct more complex molecules from widely available chemical feedstocks. Now conceptually, you can think about taking a widely available chemical feedstock, like an alcohol, and dehydrogenating that to obtain hydrogen, as well as a much more reactive aldehyde or ketone that can be further functionalized to generate a new carbon element bond. That molecule of hydrogen that was just lost during the dehydrogenation process can then be reintroduced to hydrogenate that new bond. In doing so, you've just transformed something very cheap with limited value into something much more useful, all enabled by simple reactions with hydrogen. We've developed some excellent hydrogen transfer catalysts, which are now commercially available, that dehydrogenate a wide variety of alcohols and amines into really useful compounds. These catalysts are so active that you just sprinkle in a dash of the catalyst into a solution of alcohol, heat it, and hydrogen just bubbles off as the chemical transformation takes place. We've used these catalysts to start tackling chemical synthesis sustainability and energy-related problems. We've applied the hydrogen borrowing methodology to convert ethanol to butanol. Ethanol can be produced by fermenting pretty much anything, including non-edible plant waste, which is known as biomass. However, the energy density of ethanol just isn't really high enough for it to be used as a fuel additive in large amounts. We've been able to increase the energy density of this alcohol by converting it to butanol, which, in contrast to fossil fuels, may be used as a renewable drop-in fuel additive or supplement. To address some of the grand challenges of our time, I think we need to provide students with a solid foundation of the scientific process, as well as to create an environment that promotes divergent thinking and creative problem solving. I'll say that it's pretty exciting to see students really dig deep and then have it pay off with a new hot result or a discovery that can then translate into a big advance for the field. And it's in the pursuit of these results that we're driven to explore, create, and catalyze new chemical reactions that can actually benefit humankind.